Today we will be talking about light as an electromagnetic wave. How this concept originated with the light as an electromagnetic wave, we will see together. So basically, you all know that light is a dual nature. Sometimes it behaves like a wave, and sometimes it behaves like a particle. And if you want to distinguish practically these two concepts, you can have a look at what you used to have studied previously. If we see the young double slit experiment, we have a light source. There are two slits. And on this screen, we get the interference pattern in the region of the crossover. Whereas if we take the concept of the photon and we place the photon detector, which are like point-like objects here, they will record the incident photon. They are not going to record the crossover behavior, the superposition behavior of the waves. Although the technology has given us the continuous photon detectors, which can show the photocurrent is striking in the interference region, but exact pattern can be obtained by this photoelectronic devices. So that means that we have a wave nature of the light, which correctly describes this kind of phenomenon. So before coming to the concept, let's have a brief of what you have studied about the wave. This is a wave that you all must have seen, and basically wave is a form of disturbance. So the distance between the two maximas, the two consecutive maximas, is called the wavelength. The point of maxima is called crest, and the point of minima is called trough. The distance between two successive troughs is also the wavelength. And the maximum displacement, that is the distance from the axis to the crest, or distance between from the axis to the trough, is called the amplitude, which denotes the maximum displacement. See, this is how a wave travels. Since we have talked wave in terms of the disturbance, so there was one scientist called Huygens who said that each point on the existing wavefront can be considered to as a source of light, a source of waves. You can see there are number of points, and one disturbance from each point is is coming up. There is a plane wave incident on this kind of a pattern, and what is the output? You can see that the individual disturbance or individual wave is coming from each point. And the number of the waves are dependent on the number of the points. Here there are more points, so more number of waves. Lesser point, less number of waves. So you have 1 point, so one wave. So how this thing came into picture? It was in the first half of the 19th century that established the wave theory of the light. And the nature of the light was not yet revealed, and the identity of the wave oscillations was a mystery. And this situation changed dramatically in 1860s when Maxwell came out with a theoretical treatment linking the electricity, magnetism, and optics. He linked the concepts of the electricity, the electric field, the magnetic field, and optics. So basically, he described light as a propagating wave of electric and magnetic fields. And he predicted that the existence of the electromagnetic radiation coupled with the electric and magnetic fields traveling as waves at a speed equal to the is known speed of light. So he conceptualized that if light is traveling in this direction, it is a result of two waves. It's a superposition of the two waves of traveling together. One is the electric field wave and the other is the magnetic field. This is what he visualized. The light is propagating in the x direction. There is one wave oscillating in the y direction and one in the z direction. And any of them can be an electric and a magnetic field. And he postulated that all the three will be perpendicular to each other. That means the direction of propagation, both the electric and magnetic fields are perpendicular to each other and also perpendicular to the direction of propagation. This is how a wave travels. This is a similar diagram like we were having in the previous figure. And actually, while moving, a point on the wave traces a circle. So such kind of a wave is a circularly polarized. Here, the amplitudes of the electric and the magnetic waves are equal. If the amplitudes are not equal, it will trace an ellipse and it will be an elliptically polarized. In 1888, Hertz showed the existence of long wavelength electromagnetic waves, and he also showed that the properties are in consistence with the shorter wavelength visible light. This is the famous Hertz experiment that you have already studied. So, how this concept came into focus that light is nothing but a combination of the electric and magnetic fields. So, as I said, that Maxwell was a pioneer in this idea, and before that, it was William Gilbert who initiated the magnetic phenomena in the late 16th century. And in the late 1700s, an understanding of the electric phenomena was pioneered by Benjamin Franklin, Augustine, and some others, Laplace and Gauss, who formulated their theories about electricity and magnetism. And altogether, they developed a powerful mathematical description of electrostatics and magnetostatics. And the first connection between the electric and magnetic field was given by Oersted in 1820 when he found that the electric currents produce magnetic fields in terms of the magnetic forces. And after that, Mary Ampere developed a mathematical formulation relating currents to the magnetic field, that is the source current, he called. And after that, Michael Faraday discovered the electromagnetic induction, in which a moving magnet induces an electric current in the conducting circuit. And all these activities by the Ampere, Gauss, Faraday, and all the earlier scientists resulted in the Maxwell's equations, which form the basis of the modern electromagnetic theory. And Faraday visualized the electric charges as producing fields. He postulated that the fields are manifestation of the charges, and there must be some charge behind a field. And these fields extend through space and transmit electric and magnetic forces to large distances. And this notion of the electric and magnetic fields is central to the theory of the electromagnetism. And if you take a simple quantity and take a postulate that a field is used to represent a physical quantity which changes from time to time, or with changes with space. This space and time are related. So there is a quantity which is changing. And if there is a change in any of the properties of the wave, like say temperature. So what you have to measure the temperature at many points on the wave, on the path, and you can construct the variation of the temperature, which will give you an idea of the wave is traveling. But since temperature is a scalar field and it requires only a one specific value at a point, while vector fields, on the other hand, are the physical quantities that can have direction and magnitude both. So, getting knowledge of the velocity of the wave will give us the vector fields. So, coming to Maxwell's equations, Maxwell completed the study of the electric and magnetic phenomena. He combined the two concepts and evolved the wave theory. So, initially by Faraday's law, before Faraday, it was known that the electric charges are source of electric fields and currents, which are also sources of magnetic. Faraday's law of electromagnetic induction showed that there is a second source of electric fields, that is the changing magnetic. And it was a significant development. And Maxwell postulated that changing electric fields are sources of magnetic fields. So in its modern form, the Maxwell's electromagnetic theory is expressed in the four partial differential equations for the electric and magnetic fields, and these equations are known as Maxwell's equations, and they are derived from four basic laws of the electromagnetic theory. And the manipulation of these four equations leads us to the wave equation for the field, which in turn gives us the dispersion of the field, that is the behavior of the fields in any medium. So the changing magnetic field produces electric field and changing electric field produces magnetic field. This implies that the possibility of electromagnetic field in which changing electric field continuously gives rise to a changing magnetic field and vice versa. We can have the electric field from the magnetic field and magnetic field from the electric field if there is a change in the magnitude. So electromagnetic waves do not represent physical displacements that propagate through a medium. It's only the not like mechanical and water waves, which are waves are moving through the medium. These only describe the propagating oscillations in the strengths of the electric and magnetic fields. So Maxwell's equation showed that the speed of the waves is that of the speed of the light that was known at that time. And it's determined by a combination of the constants and the laws of the electrostatics and the magnetostatics. So the four basic equations were, the first one was the Gauss law. Second one was the magnetic monopole, del dot B is equal to 0, signifying that magnetic monopoles do not exist. You ought to have a north-south pole together. In isolation, north can't exist, and in isolation, south can't exist. The third equation was the Faraday's law, and the fourth equation was the Maxwell's law. Ampere's law, it was Maxwell's modified it, and the modification we will study later. So considering the first equation, He said that the electric flux through a closed surface is proportional to the total charge enclosed by the surface. The total flux is proportional to the total charge enclosed. So this is Gauss law. The second equation is also a form of Gauss law, but with magnetic flux instead of electric. And it says that the field lines that leave the surface of the North Pole must enter back through the south to reach, to enter from the surface to reach the south. You can see the lines which are coming out from one pole, goes back and enters the other. The third one is the Faraday's law, which says that a changing magnetic field will induce the electromotive force in the loop of a wire. And the fourth equation is the Ampere's law that the current carrying wire induces a magnetic field around the path surrounding the wire. And if you design an experiment like this and put iron fillings, you will say that they are deposited on the magnetic lines of force. So basically, after knowing the properties of light in different medium, in different regimes, and especially a scale was prepared on the magnitude of the wavelength of light. That is called the electromagnetic spectrum. So the lesser the wavelength of the light, the more energetic it is, because the energy is equal to Hc upon lambda. It is inversely proportional to lambda. So the least energy is of the highest wavelength, and the lowest wavelength will have the maximum. So if we start on the basis of the electromagnetic spectrum on the basis of the wavelength, the lowest wavelength is of gamma ray, which is of the order of 10 to the power minus 12 meter. And if you compare the sizes, it is the size of an atomic nuclei. The dimensions of the wavelength are of the size of an atomic nuclei. As we increase the wavelength, we come into X-ray regime that is of the order of 10 to the power minus 10 meters. And this is dimensions are comparable to the dimensions of an atom. If we can increase the wavelength by 2 orders more, we have 10 to the power minus 8 meters, and the dimension now becomes the dimensions comparable to the dimension of the molecule. And if we increase further by 2 orders, it is 10 to the power minus 6 meters. These become of the order of the single cellular organisms like protozoa and all. And if we increase further by 1 order, we come to a tip of a needle, the micrometer size. And if we come to the order of 10 to the power minus 2 meters, it is the microwave region, which are the sizes of the butterfly. And 10 to the power 1, that is the size of the human being. We have a height of nearly ranging from 1.5 meter to 2 meters. It depends. 2 meter is quite high. So it's about 1.5 meter. And if we increase the wavelength further, we go into radio waves. Which are of the order of the magnitude of the buildings. You can also compare that with these with other objects. And these regions are now called. This was the lowest wavelength was the gamma ray. If we increase 2 orders, it is X-ray. Again, 2 orders, we get ultraviolet, then visible, then infrared, then microwave, and then radio. radio waves at the highest wavelength and the lowest energy. So by the wave concept, we are able to explain diffraction of light. We can explain refraction, interference, dispersion, reflection, and polarization of light. So this is all for today.